The first kind of non-volatile memory we will discuss is EPROM, where E stands for electrically and PROM stands for programmable ROM. So this is an electrically programmable ROM, and it is specifically only electrically programmable, meaning that it is not electrically erasable. This means that we can program a 0 into a cell by causing the transistor to not exist by raising its V threshold in situ when the transistor is being used on the chip. But we cannot deprogram it or erase it while the chip is being used. So this is how the device for EPROM looks like. And for all NVMs, what we will be interested in is first the device used, which allows us to see how it is programmed and deprogrammed, and then the array, the memory array of the ROM itself. For EPROMs, the memory array is basically a no ROM, and it is read from exactly the same way we read from any no ROM. But it's how it is programmed that really is of interest to us. So basically what happens is you apply a normal supply voltage on the drain, and you apply a very high positive voltage on the gate. This high positive voltage, called the programming voltage, does two things. First, it creates a channel, and the electrons in this channel are kind of energetic. But the positive voltage also creates a vertical field which attracts the electrons into the oxide. This causes the electrons to flow through the oxide, causing it to break down through avalanche breakdown. And this avalanche breakdown leads to a large electron flow into the floating gate. This device is called the famous device, and this stands for floating gate, this is the F, avalanche injection, this is the A, MOS. So this is a floating gate avalanche injection MOS device. So if you want to program a certain cell in an EPROM to carry a 0, you have to do this. Now, all the cells by default are carrying a 1, and by programming certain cells to carry zeros, we can write data into the memory array. The problem with EPROMs is that you can program them using specific electrical values on the gate and the drain, but you cannot erase them by applying electrical values to the gate and the drain. The problem here is that the oxide below the floating gate and the oxide between the floating gate and the control gate are thick. And this device is of historical interest. It's no longer practically used, which is why the oxides were kind of thick. So we don't have any mechanism by which we can push back the electrons from the floating gate down into the substrate. And so what you would do if you want to erase an EPROM chip is you have to take it out from the assembly. You have to put it in a special machine that exposes it to ultraviolet light, which is why EPROM chips usually have a transparent window on top that allows the die to be exposed to UV light when you want to erase it. And so you cannot erase it while it is on board on the PCB. You can't even erase it at home because it requires a specialized device to erase it. And more importantly, when you erase it, you erase everything on it. You reset it so that every cell is carrying a logic 1 instead of any specific data. And so you cannot erase a specific cell. You have to erase everything on the chip at once. This is one huge disadvantage of EPROMs, which is that you can program them only once, and then you have to do a very arduous task to deprogram them, to erase them. And so they're not suitable, obviously, for mass storage as, the quote-unquote hard disk of a mobile phone, for example. The other disadvantage is that the avalanche injection operation is first very, very harsh on the oxide. So this reduces the number of times you can program the chip. And also it's very slow. So programming is kind of slow. But what's even slower is erasure. So, okay, you have to put it under a UV light. And what the UV light does, by the way, is it frees some of the electrons in in the oxide, thus making the oxide more or less conductive, and thus allowing electrons to drop down from the floating gate into the substrate. And that process not only requires specialized equipment, but is also very slow, which is why we no longer use EPROMs, and for a very long time we have not used EPROMs. Instead, the next practical thing we can do is to use double EPROMs. Now these are programmable ROMs, which are electrically erasable and programmable. So this is electrically erasable programmable ROM. So you can do both things. You can program the transistor, which means you put electrons on its floating gate, causing it to store a 0, and you can erase it by removing the electrons from the floating gate, causing it to store a 1. You can do both things by applying specific electrical values to the cell. And so this is the storage device used in double EPROMs, and it's called the Floatox device. So Floatox stands for floating gate tunneling oxide. And when you look at it, it's actually not a single device, it's actually a couple of MOSFETs. So there's this MOSFET, which is actually a run-of-the-mill MOSFET, and we call this the access transistor. And so you see we have an access transistor here. And then there's the storage transistor here, which is kind of a little bit strange because it has a double gate, which is something we expect because it has to have a gate on which it can store electrons. And also the gate takes a bend down towards the substrate near the drain. And also the gate extends a lot over the drain. The gate extends significantly over the drain of the transistor. So this is called the storage transistor, and its gate has a terminal called P, where P stands for programming. When we use a lot of these transistors to make an array, you can see the array here, and the array is basically a no-ROM. So we are using a no-ROM array structure because everything is in parallel with each other. Now, when we look at this array, we can immediately see the disadvantage of double EPROMs, which is that there are 2 transistors per cell. And this is really bad because when we talked about no ROMs, we said that their density was not good because they used multiple ground lines, and which is why NAND ROMs are better. But this is even worse because each cell now has 2 transistors instead of 1 transistor, in addition to needing multiple ground lines. But you will notice that when you have here in the array, you have word lines, and the word lines are connected to the gates of the access transistors. And you have programming lines, and the programming lines are connected to the gates of the storage transistors. And these are the bit lines, right? So let's consider how we program a specific cell. So here in this diagram, we are programming cell 0, 0. So if you look at cell 0, 0, we have activated word line 0 and deactivated all the other word lines. This causes the access transistors of all the cells in the first row to be active, but we are going to apply a VDD only to the bit line of the first column. And therefore, when we apply a 0 to the bit lines of all the other columns, it really doesn't matter that the access transistors are on, because all that's going to happen is that these access transistors are going to pass a 0 to the internal node between the storage transistor and the access transistor. We also apply a very high positive voltage VPP to the programming terminal of the first row to programming 0. And therefore, if you look at the first storage transistor, what's happening here is that it has a VDD transferred to the internal node. It should be VDD minus V threshold because there's a V threshold loss, but that's okay. And it has a VPP applied to the gate. So what's going to happen here is that there will be a voltage of VDD to this terminal, a ground to this terminal, and a very large VPP voltage to the gate. This very large VPP is going to create an extremely healthy channel, in the storage transistor, and the VDD applied to the drain is going to cause electrons to move through the transistor. These electrons will be very energetic when they reach the drain, which allows them to have enough energy to go through the oxide using the hot carrier effect. There is a large vertical field created by VPP that promotes this process, and therefore we will attract a lot of electrons into the storage gate using the hot carrier effect. Now, the hot carrier effect will allow us to program the storage transistor really fast, and it also is much gentler on the oxide than avalanche breakdown, which was used with famous devices. So we managed to program specifically this transistor. None of the other transistors in the row will be programmed because none of them will have a current flow. Even though they have VPP applied, they don't have current because they don't have a drain voltage applied. So the electrons within them are not energetic enough to cross the oxide by the hot carrier effect. None of the transistors in the other rows will also be programmed because they have 0 applied to their word lines. So we are programming specifically cell 00. Now, how do we erase a cell? Which means we remove the electrons from the floating gate, push them back into the substrate, and the cell is now storing a 1 instead of a 0. Here we are erasing cell 00 specifically, which is the cell we just programmed. And the way we do this is, again, we apply VDD to the word line, thus enabling the access transistor. This will enable the access transistors in all of the row. And then we apply VPP to the bit line. So we apply a really large positive voltage to the bit line. What this is going to do is the VPP is going to pass to the drain of the storage transistor, the VPP, the high voltage VPP, and we are applying 0 to its gate. Now, what's going to happen here is that the gate has a 0 voltage, and the drain terminal here has VPP applied. This is going to cause tunneling to happen on the drain side, but the tunneling is going to be from the drain down to the substrate, because the field is in the opposite direction to the direction we are used to. So we're going to have electrons tunneling down from the gate into the substrate, which is why we had the floating gate take this sharp turn down on the drain side. This allows the oxide to be very thin near the drain, which promotes tunneling at the drain side. But keeping the oxide thick for the remainder of the channel allows us to have more control on how much tunneling happens within the rest of the channel. And so we can localize the tunneling that happens to the drain side only. Now, if you look at the other cells in the row, these cells are not going to be programmed or erased because they don't have VPP applied to their drains. They have zeros applied to their drains. Now, the other cells in the column are also not going to be erased because even though they have VPP applied to the drain of the access transistor, the access transistors are disabled by applying 0. So this array, the EPROM array, double EPROM array, is really good because it uses hot carrier injection for programming, tunneling for erasure, which are both gentle on the oxide and thus allow high write cycles. But it has a problem, which is that it contains 2 transistors per cell. And the reason it has to have 2 transistors per cell actually has to do with erasure. So if we imagine that we have an array that contains only the storage transistor, we don't have an access transistor at any cell, then let's just repeat the structure, the setup we used for programming, which is this. And here we are interested in programming cell 00. So we're going to have a current through the channel of this storage transistor. We're going to have a large vertical field, and there will be hot carrier effect, and the cell will be programmed. Now, all the other cells in the column are not going to be programmed because they have zeros applied to their gates, which is great. We don't want them to be programmed. We want to program a specific bit. But what happens to all the other cells in the row? Now, all the other cells in the row don't have a current within their channels, right? Because they have 0 applied to the bit lines, and so there's no VDS, there's no current. Since there's no current, then there's no hot carrier effect. However, there's a VPP applied to the gate of these transistors. And this very large VPP is going to cause tunneling in these transistors. And so maybe with the application of VPP to the gates of these transistors, even with no current in the substrate, maybe you're going to attract some electrons into the floating gate and thus accidentally programming some of these cells. Yes, that's an issue, but it's actually kind of a secondary issue. It's not a huge deal because hot carrier effect is much faster than tunneling. So the amount of time it takes for this cell to be programmed is going to be much shorter than the amount of time needed for any of the other cells in the row to program using tunneling. In other words, while programming this cell, the effect on the threshold voltages of all the other cells in the row from tunneling is going to be negligible. So actually there's no problem programming using this method. The real problem is actually with erasure. And so if we look at the erasure structure that we use to erase cell 0, 0, now we have VPP applied to the drain of the storage transistor and 0 applied to the gate, which creates a negative vertical field that promotes the motion of electrons from the gate into the substrate. Now, none of the cells in the first row are going to be erased. None of them are going to suffer from any deviation in their threshold voltage because they actually have nulls on all their terminals. They have nulls on the drain, on the source, and on the gate. So all the cells in the first row are safe. The problem is with cells in the first column. All the cells in the first column observe the same terminal voltages as the cell we want to erase. There's no distinction between the terminal voltages seen in cell 01 and in cell 00, in cell 10, and in cell 20. So these three cells are going to observe the same terminal voltages, which is VPP on the drain, 0 on the gate, and 0 on the source. So tunneling, which is the process through which we deprogram or erase the first cell 0, 0, is also going to happen in cell 10 and in cell 20. So if any of these cells contained any information, that information will be 0. That information will be erased. And so there's no way we can erase a single cell if we don't have an access transistor. We have to accept the fact that we are going to erase a lot of cells as a bunch together with each other. But one question one might ask is, did this not also affect EPROMs, single EPROMs, using famous devices? Yes, it did. But in EPROMs, we really didn't care about this because when you wanted to erase a specific cell in the array, you had to take the whole chip out, put it under UV light, and erase everything on the chip. So yes, you couldn't erase a single cell. You actually only had the ability to erase everything on the chip at once. But this is an important conclusion that we reach here, which is that if we insist on having a single transistor per storage cell, then we have no way of erasing a single cell. And we have to accept the reality that when erasing a single cell, we would have to erase all the other cells, at least in the column that share the same bit line with it. This is actually the foundation of flash memory, which is the most important and most practical category of non-volatile memories.